So in this video we're going to prove that the Moivre theorem is true for negative integers, given of course that it's true for positive integers, which we've previously proved using induction. So what we're proving, let's write down what we're trying to prove first of all. So we're trying to prove cos theta plus I sine theta, so to the n is equal to cos n theta plus I sine n theta, where n is a negative integer. Alright, so let's make it clear that this is what the proof is here. So I do see people writing down what they're needing to prove, and it kind of merges with the proof. So if you must write down the line that you're trying to prove, then make it clear that where the proof starts, because it's an absolute cardinal sin to actually use what you're actually being asked to prove the result, which of course is totally flawed mathematically. If you're trying to prove something, you can't use it to prove it. And I saw someone do something like this relatively recently. I'll tell you when. It wasn't actually at the beginning, it was later on. So what we want to do is we want to prove that, so we've got cos, so we're going to consider cos theta plus I sine theta to the n. N is a negative integer. Okay, and we're with a negative integer. Okay, so that's equal to 1 over cos theta plus I sine theta to the m if we let n m equal to minus n. So now where n is a positive integer, m is a positive integer. Now we can use de Moivre's proof here because we are assuming it's true, and we did prove it inductively in the previous video. We can use de Moivre's here. So that's 1 over cos m theta plus I sine m theta. Now this is where the mistake I was referring to earlier, where I think it was last year, where someone now then basically called this to the power minus 1 and brought it back up to the top. Of course, complete nonsense, because that's assuming de Moivre's theorem is true for this value, and it works in that way. So we're trying to prove that effectively. So that would be actually proving using something that we don't know yet is true until we proved it. So what we did was just multiply by the complex conjugate on top and bottom. Let me just make a bit. Okay, so let's go up here. We can then multiply by the complex conjugate on top and bottom. So that's 1 over cos m theta plus I sine m theta times by cos m theta minus I sine m theta on the bottom. And then on the top, the same thing, of course, minus okay. So now when I multiply this out at the bottom, we're going to find it's a difference of 2 squares, and we're going to find quite nicely we need an m there, of course, and I needed an m there. Let's rewrite that there. Cos m theta. And we need an m there. Okay. All over cos squared m theta plus sine squared m theta. Now that bottom is equal to 1, so that's equal to cos m theta minus I sine m theta. Right, now obviously we started off with n, so we go back to that. Now what m is equal to minus n, we said, so that's equal to cos minus n theta minus I sine minus n theta. Now because cos is an odd function, we can write it down here. We've got cos is odd, so in other words cos x is always equal to the cos of minus x. It's symmetrical about the y-axis, and sine is an even function. Cos is an even function. Apologies if I said that the wrong way around. Cos is an even function, and sine's an odd function, because sine of x, because it's got is equal to minus sine of minus x is equal to minus sine of x. Okay, so what that means is that's equal to cos n theta plus I sine n theta. And so that's it. So that basically means, if I rub all this out now, because that basically means that de Moivre theorem is true for negative integers if it's true for positive integers, which we've already proved anyway. So it's true. It is true for negative integers. But that's the nature of these proofs. I've kind of come in the middle of this, so we can actually say it's true for negative integers because we've already proved it's true for positive integers. Okay, so that's it. That is something that could be asked in the Edexcel exam. I'm wondering if it did, whether it would whether the wording would be something like this. Because it's unlikely they'd ask you to go through the whole thing proving it for negative integers, because then really you'd have to do the inductive proof that we proved for positive integers and then go on to do this, which would be quite long. So I'm thinking that they would probably just expect this, and the wording may be similar to the wording I've used here, saying prove that de Moivre theorem is true for negative integers, given that it's true for positive integers, or something of that ilk. Okay, that's it.